Dynamic insertion policy. For some applications, BIP has fewer misses than LRU, and for some, LRU has fewer misses than BIP. We want a mechanism that can choose the insertion policy that has the fewest misses for the application. We propose a mechanism that dynamically estimates the number of misses incurred by the two competing insertion policies and selects the policy that incurs the fewest misses. We call this mechanism dynamic insertion policy. A straightforward method for implementing DIP is to implement both LRU and BIP in two extra tagged directories. Data lines are not required to estimate the misses incurred by an insertion policy and keep track of which of the two policies is doing better. The main tag in directory of the cache can then use the policy that incurs the fewest misses. Since this implementation of DIP gathers information globally for all the sets and enforces a uniform policy for all the sets, we call it DIP global. The DIP global mechanism. Figure 9 demonstrates the working of DIP global for a cache containing 16 sets. Let MTD be the main tag directory of the cache. The two competing policies, LRU and the BIP, are each implemented in a separate auxiliary tag directory. ATD LRU uses the traditional LRU policy and ATD BIP uses BIP. Both ATD LRU and ATD BIP have the same associativity as the MTD. That axis stream visible to MTD is also applied to both ATD LRU and ATD BIP. A saturating counter, which we call policy selector, P-cell, keeps track of which of the two ATDs incurs fewer misses. All operations on P-cell are done using saturating arithmetic. A miss in ATD LRU increment P-cell and a miss in ATD BIP in decrements P-cell. The most significant bit MSB of P-cell is an indicator of which of the two policies incurs fewer misses. If MSB of P-cell is 1, MTD uses BIP. Otherwise, MTD uses LRU. Implementing DIP via set dueling. The DIP global mechanism requires a substantial hardware overhead of two extra tag directories. The hardware overhead of comparing two policies can be significantly reduced by using the dynamic set sampling concept proposed in one of the paper. The key insights in DSS is that the cache behavior can be approximated with a high probability by sampling few sets in cache. Wait a minute, just a minute. I have to fix something. The hardware overhead of comparing two policies can be significantly reduced by using the dynamic set sampling concept proposed in the key insights in DSS is that the cache behavior can be approximated uh, with a high probability by sampling few sets in cache. Thus, DSS significantly reduced the number of ATD entries in DIP Global from thousands of sets to about 32 sets. Although DSS significantly reduces the storage required in implementing the ATD to around 2 KB, it still requires building the separate ATD structure. Thus, implementing DIP will still incur the design, verification, and testing overhead of building the separate ATD structure. We propose set dueling, which obviates the need for a separate ATD structure. The scheduling mechanism dictates few sets of the cache to each of the two competing policies. The policy that incurs fewer misses on the dedicated sets is used for the remaining follower sets. An implementation of DIP that uses set dueling is called DIPSZ. Figure 10 demonstrates the working of DIPSD on a cache containing 16 sets. Set 0, 5, 10, and 15 are dedicated to the LRU policy, and sets 3, 6, 9, and 12 are dedicated to BIP policy. The remaining sets are follower sets. A miss incurred in the sets dedicated to LRU increments P cell, whereas a miss incurred in the sets dedicated to BIP decrements P cell. If the MSB of P cell is 0, the follower sets use the LRU policy, otherwise the follower sets use BIP. Note that set dueling does not require any separate storage structure other than the single saturating counter. DIPSD compares the number of misses across different sets of two competing policies. However, the number of misses incurred by even a single policy varies across different sets of in the cache. A natural question is how does the per set variation in misses of the component policies affect the dynamic selection of set dueling? Also, how many dedicated sets are required for DIPSD to approximate DIP global with a high probability? In Appendix A, we derive analytical bounds for DIPSD as a function of both the number of dedicated sets and the per set variation in misses of the component policies. The analytical model shows that as few as 32 to 64 dedicated sets are sufficient for set dueling to select between LIP and BIP with a high probability. In section 5.4, we compare the misses incurred by DIPSD and DIP Global. Dedicated set selection policy. The dedicated set for each of the competing policies can be selected statically at design time or dynamically at runtime. In this section, we describe our method of selecting the dedicated sets. Let n be the number of sets in the cache and k be the number of sets dedicated to each policy. In our studies, we restrict the number of dedicated sets to powers of 2. We logically divide the cache into k equally sized regions, each containing n by k sets. Each such region is called a constituency. One set is dedicated from each constituency to each of the competing policies. Two bits associated with each set can then identify the set as either a follower set or a dedicated set to one of the two competing policies. We employ a dedicated set selection policy that obviates that need for making the leader set in each constituency on a per set basis. We call this policy the component complement select policy. For a cache with n sets, the set index consists of log2n bits, out of which the most significant log2k bits Identify the constituency and the remaining log to n by k bits. Identify the offset from the first set in the constituency. The complement set policy dedicates to LRU all the sets for which the constituency identifying are equal to the offset bits. Similarly, it dedicates to BIP all the sets for which the complement of the offset equals the constituency identifying bits. Thus, for the baseline cache with 1024 sets, if 32 sets are to be dedicated to both LRU and BIP, then complement select dedicates set 0 and every 33rd set to LRU and set 31 and every 31st set to BIP. The sets dedicated to LRU can be identified using a 5-bit comparator for the bits 40 to bits 95 of the set index. Unless stated otherwise, the default implementation of DIP is DIP-SD with 32 dedicated sets using the complement or select policy and 10-bit P-cell counter. In the paper, one of the paper, a Bernoulli model is used to derive the bounds for DSS. However, as they used an ATD, they were comparing two policies by implementing both policies for a few sampled sets. Their analytical model does not consider the per set variation in misses incurred by the component policies. However, in our case, set dueling compares the component policies by implementing them on different sets in the cache. Therefore, the analytical model for set dueling must take into account the per set variation in misses incurred by the component policies. Therefore, the bounds derived in one of the paper are directly applicable to set dueling. This is the graph. It is a reduction in L2 MPKI percentage using the BIP, DIP Global, DIP SD, DIP SG, N62 and N64, 32 and 64. So let's see, go ahead. Figure 11 shows reduction in MPKI with BIP, DIP Global, and DIP SD with 32 and 64 dedicated sets. The bar labeled a mean is a reduction in arithmetic mean. MPKI measured over all the 16 benchmarks. DIP Global retains the MPKI reduction of BIP while eliminating the significant MPKI increase of BIP on equate, benchmarks equate, parser, mgrid, and swim. With DIP Global, no benchmark incurs an MPKI increase of more than 2% over LRU. However, DIP Global requires a significant hardware overhead of about 128 kb. DIP SD obviates this hardware overhead while obtaining an MPKI reduction similar to DIP Global for all benchmarks except T-Wolf. As the number of dedicated sets increase from 32 to 64, the probability of selecting the best policy increases. Therefore, DIP SD with 64 dedicated sets behaves similar to DIP Global or T-Wolf. However, having a large number of dedicated sets also means that a higher fraction n by small n by capital N of sets always use BIP. Even if BIP increases MPKI, uh, this causes the MPKI of swim to increase by 5% with 64 dedicated sets for A and MP. DIP reduces MPKI by 20% even though BIP increases MPKI This happens because in one phase LRU has fewer misses and in the other phase BIP has fewer misses. With DIP, the cache uses the policy best suited to each phase and hence a better MPKI than each of the component policies. We discussed the dynamic adaptation of DIP in more detail in section 5.5. For an average, DIP Global reduces average MPKI by 22.3%. DIP SZ with 32 dedicated sets reduces average MPKI by 21.3%, and DIP SZ with 64 dedicated sets reduces average MPKI by 20.3%. Adaptation of DIP to application. DIP can adapt to different applications as well as different phases of the same application. DIP uses the P cell counter to select between the component policies. For a 10-bit P cell counter, a value of 512 or more indicates that DIP uses BIP. Otherwise, DIP uses LRU. Figure 12 shows the value of the 10-bit P cell counter over a course of execution of the benchmarks MEMCF, ART, Health, SWIM, and AMMP. We sample the value of the P cell counter once every 1 million instructions. The horizontal axis denotes the number of instructions retired in millions, and the vertical axis represents the value of the P cell counter. For MCF, the dip mechanism almost always uses BIP. For health, the working set during the initial part of the program execution fits in the baseline cache and either policy works well. However, as the dataset increases during program execution, it exceeds the size of the baseline cache and LRU causes thrashing. As BIP would have fewer misses than LRU, the P cell value reaches toward positive saturation and DIP selects BIP. For the LRU friendly benchmark swim, the P cell value is almost always towards the negative saturation, so DIP selects LRU. AMMP has two phases of execution. In the first phase, LRU is better, and in the second phase, BIP is better. With DIP, the policy best suited to each phase is selected. Therefore, DIP has better MPKI than either of the component policies standalone. P cell value during benchmark execution. Horizontal axis denotes the number of instruction million.